Hey everyone, thank you so much for checking out a new Weaviate release podcast, releasing Weaviate version 1.15. This release is chocked with all sorts of exciting new things from cloud native backups, improved stability for high memory setups, faster imports for ordered objects, more efficient filter aggregations, two new distance metrics, two new Weaviate modules, and then smaller improvements and bug fixes. So it's a long list of exciting new things. To me, I think it's so interesting seeing these concepts in computer science, like red-black trees, and how do they impact database systems? How has it been added to Weaviate and all these other exciting things? Etienne's written this awesome article on the GOMEMLIMIT and how that's improving the stability for high memory setups, and then this cloud-native backups. So Etienne, thank you so much for coming on the Weaviate podcast to discuss version 1.15.
Hey, Connor, thanks for having me. Yeah, it's a super exciting release. So many cool new features. When we initially set out to build this 1.15 release, the main plan basically was around backups. But now we have this long list of features, and I think every single one of them is a great reason to upgrade. But yeah, let's maybe start with backups. They're the kind of point, yeah, everyone needs backups, right? I mean, it's kind of a requirement to run your database in production or any stateful load such as database. And you could do backups before. You could kind of do them before because you could do them at an infrastructure level, basically manually. Weaviate writes its files on disk, so you could take a snapshot of that particular disk and store it somewhere, do it with your cloud provider. But that's not a really smooth process. This would basically give you vendor lock-in for that specific vendor, so you could really migrate. You would be kind of left, or you would leave Weaviate in this kind of weird state where it wasn't really ever prepared to take copies of files. So on restore, you would get these like weird error messages. Did Weaviate crash? Is it trying to recover? So it was kind of possible, but it just wasn't a very good user experience. And Weaviate is all about user experience. So now we've kind of done the exact same opposite, and now we have a backup feature with a user experience that we're absolutely proud of. With the 1.15 release, you can back up and restore it to any cloud provider or to your local file system. So we have support for AWS S3 or any S3 implementation. Actually, it doesn't have to be the AWS one. It could also be an open source one, for example. For Google Cloud, GCS, for a local file system, and basically these can all be plugged in using Weaviate's module system. And then you can just do a single command. We have support for this in all of our clients and all of our language clients, or you could just send a raw HTTP request to start a backup, and that's it basically. And Weaviate will do all the cool things in the background, and it's been engineered to be minimally intrusive basically. So you can keep using Weaviate, and in fact, we encourage you to do this in production and basically keep running Weaviate in production, send requests, have your users use the machine. They can even send write requests in the way that it's architected without any kind of impact. And the backups will just run in the background, and then you can restore them either onto the same machine or even onto a different machine if you like.
Yeah, and I think that the UX, the design and the documentation that shows you how to do it is so well communicated, and really, massive credit to how you've written how Weaviate stays running all the time, how you can select certain classes. And I want to get right back to the UX, but this little story about not backing up your data, I really like this HBO show, Silicon Valley. I imagine like a lot of our listeners maybe have seen this show and enjoyed this show. And there's a scene where Richard he hasn't backed up the data. They have like this insurance client, Dan Melcher, and they're all panicking that we have no backup of our data. And then they try to like migrate their server to Stanford, and it falls apart, but then the system's backed itself up on the refrigerators. And it's this really funny scene in that show, but kind of communicating that urgency of like, you need to have your data backed up.
Exactly. You do. And Weaviate gives you a proper way to do that. Now, no refrigerators involved at all.
Yeah. And so one thing about the UX is I was curious about this notion of backing up specific classes. So I imagine I have like 60 classes and I only want to back up some of them. And the UX makes it so clear of how you include certain classes. And can you tell me about the design decisions behind that part of it?
Yeah, absolutely. So this is actually mainly based on user feedback. So the entire feature was developed around users' input. Like, of course, you ask your users before you write the first line of code, and then you try and get feedback. And this is something that was very, very heavily influenced from community feedback. So basically, the idea behind the backup system is I think there are so many use cases that you can do. Like, you can even use it to migrate between environments and these kind of things. But generally, I see two main use cases for a backup. Like one is the disaster recovery case, where basically the disk is lost, or someone deletes it, or this kind of. So basically, to take all the data, be very agnostic of what data is on there, and just take the whole thing, basically back it up and restore it. That's one option. The other option is basically more at a logical level, where you know what your specific classes mean, and you want to create a backup, not so much to protect against hardware failure or cloud provider failure, but against user errors. So, for example, a user could accidentally delete data just through the API. So if you want to protect against that, then you would do a sort of, would also do a backup, but it would be more to protect against user actions and more this kind of application level backup. And there you might not want to back up the entire database. For example, of course, Weaviate can be used for all kinds of different use cases. And I know of some that use classes basically as their isolation unit for multi-tenancy. So they would have their own service that runs for their customers, and each customer would produce one or not directly, but basically their application would create one or more classes inside Weaviate that belong to exactly one customer. So maybe they have a requirement, maybe for SOC 2 or GDPR or something, that customer data needs to be stored in a specific way. So that would be one option, for example, to just create a backup for a specific class. And the API is designed in a way that it gives you three options, basically. You can provide no information at all. This way, it would just take a backup of the entire instance with everything that's on there. Or you could set an explicit list of classes. So then basically only what's included in the class would be backed up. Or you could do the other way around, where everything except basically have this exclude field, and you can say like, okay, don't exclude this, or don't include this class, basically exclude this class because it's sensitive or something, and then it would create a backup of all the other classes.
So like different classes might be, you need more like, let's back this up every hour or so, and then other things it's like, well, we need to back this up, put it behind some security because this is particularly sensitive. Yeah, I think that's really interesting.
Great point. Yeah,
think about
exactly. The timing plays a big role. Like you could have a class that rarely changes, but is maybe very large. Why would you back it up all the time? Or you could have another class that frequently changes, and you need much more frequent updates. So yeah, that's also a nice way to decouple this a bit, basically, and just give you all the flexibility to really, from a technical perspective, it's just a single call, but you can do a lot with it. You can customize it in whatever way you want.
One thing I'm kind of struggling to wrap my head around is, so when you back it up, what does the kind of state look like? And does it differ from like S3? Because S3 is just like a file storage thing, right? Or so when it's backed up, is it like a JSON or file of data? What is the backup thing?
The backup is almost an exact copy of what you would have on your disk in Weaviate normally. So it's basically the binary file formats for the LSM trees, for the HNSW index, for other index types that we have. So for BM25, for example, there's a simple index that tracks a property length, because you need these like average property lengths for the BM25 combination, and other basically metadata that we need for maintenance. So it's almost an exact copy of those files. And then there is a snapshot. I think it's actually called snapshot JSON, but that's basically just an implementation detail that gives you a bit of info about the backup itself. So it's like what kind of machine was it running on, when was the backup created, what's the ID of the backup, and these kind of things. And that's basically the metadata that makes this backup a sort of self-contained backup, I would say. And what I mean with that is basically you could create, so let's say you have two instances. One is your production instance, and the other one is, let's say, your local instance, which is completely empty. Now you want to migrate, basically using backups your data from the production instance to the cloud provider, and then basically pull back the backup from the cloud provider. Then all you have to do is send the request from the production instance, put it into, let's say, S3, in this S3 bucket. And then on your local machine, as long as it's configured to point to the same S3 bucket, you can restore that exact same backup just by specifying its ID. And the local instance doesn't need to know anything about your production instance. So you don't have to do any like pre-configuring. Basically, the backup is completely self-contained with everything that it needs to be runnable.
So, so one thing I'm very curious about is with, say, the collection of demos, and on GitHub Weaviate examples, we have things like, clip demo with the UI, and searching through movies, searching through wines, all these examples. And I love this idea of getting Weaviate demos of, here's a GraphQL API to search through Wikipedia, search through archive, maybe complete with a UI also. Would this backup, because I'm thinking about how, I think right now you clone it locally and then spin it up and have it running, would instead just kind of restoring from a backup be an easier way to run the demo yourself?
Yeah, absolutely. So basically, because the backup and restore is just copying of files. That also means any kind of index building that you have to do, that's already contained. So let's say you have this massive instance where you have hundreds of millions of objects, and it took you maybe over a day to index it. If you create the backup is just copying the files basically of all the index structures that have already been built. And then if you want to restore it, so let's say you want to run a demo case, and we've basically just put the demo data set into a backup, and you restore from that. That would make it a super fast process, because you basically just wait for the time it takes to copy the files, and once they're there, you can start it up and you can use it.
Yeah, wow, that's incredible. Then you avoid the import time and just backup. Wow. So I think that was a great coverage of backups. And for people listening, we have these 7 different things that I outlined in the beginning that are going to be chunked up in chapters. And Dirk is going to be coming on in the second half to discuss the red-black trees in this thing. But the next topic, Etienne, could we talk about the GOMEMLIMIT? You've written this great article. How does this help Weaviate?
Yeah, thank you for bringing up the article. The GOMEMLIMIT is one of those features where we really benefit from the Go language community being active and improving Go itself. So a lot of the improvements that we do in Weaviate, they're typically code that we write where we've done something that maybe wasn't ideal before, and now we've found a better way, or we've just improved it in general. So for example, the memory improvements or allocation improvements for filtered aggregations that you're talking about with Dirk later, they are something where basically we've just written better code. But GOMEMLIMIT is one of those few things basically where we didn't have to do much other than compile the binaries for the new 1.15 version with the latest version of Go, because this is a new feature that Go actually introduced. And GOMEMLIMIT is basically a soft memory limit, and soft means that Go cannot prevent your memory from growing beyond that limit. So it's not a hard limit. Basically, the kernel has a hard limit. It does an out-of-memory kill if the memory is exceeded, and that's the hard limit. But it's a target, and a target is super important for a garbage collected language, because by default in Go, the target would always be twice of what you have. So to put that in simple terms, let's say your application currently uses 2 gigabytes of memory, and you want it to use 2 gigabytes. Like, that's not accidental or temporary allocations, but that is, let's say you want to keep your vectors in memory, and this is 2 gigabytes of vectors. Then with that target being to double, so it's called 100% in Go language. Basically, it's that Go GC equals 100. That would mean that your instance can grow all the way up to 4 gigabytes. And that's relatively small number, so that might still be okay. You might have a 4 gigabyte instance. But now let's say you have this massive setup and your stable memory is 200 gigabytes. Most likely you don't have a 400 gigabyte instance just to have a buffer for temporary allocations. You would have, let's say, maybe 20% overhead, and you would have a 240 gigabyte machine. Now, if you set your Go GC instead of to double to 20%, that would work for this particular case. But you have to know exactly where you end up, which is the 200 gigabyte. You have to know exactly how much you have. And that means that to get there, you already had a basically very aggressive garbage collector, because it was set to 20%, which means you've spent a lot of time on garbage collection, which might not be something that you would want to do. And GOMEMLIMIT basically is the missing turning knob here. It's actually not a turning knob, it's maybe sort of a knob that turns itself, because it basically turns the other knob, the Go GC knob, which basically in a single sentence, the closer your memory usage gets to the limit, the more aggressive it makes the garbage collector. So in the beginning, on your 240 gigabyte machine, you have all the memory in the world. There's no reason to save memory. So Go can, for example, double the heap every time. That's fine. But at 220 gigabytes or 200 gigabytes with 240 gigabyte limit, you can't double anymore. And this is exactly what GOMEMLIMIT does in the background. It would then make the Go garbage collector quite aggressive, and then you would never sort of run out of memory again when you think you shouldn't have, because you've calculated your stable memory requirements and it was all fine. And yeah, long story short, all you have to do is set a single configuration environment variable, which is this GOMEMLIMIT, and you just put it to however memory you have. And if there is a way that the Go runtime can prevent it by basically making the garbage collector more aggressive, it's got your back, and it will take care of not going over there. What it can do, of course, is if you keep on importing and you have vectors that require 260 gigabytes of memory on a 40 gigabyte machine, that will still run out of memory. But for those cases where you kind of accidentally ran out of memory, it will prevent those. And I think that's super cool for having to do nothing but yeah, upgrading to the latest version and setting a new environment variable.
Yeah, it's super interesting. I'm not going to claim to be knowledgeable about Go really, but I've seen like these CUDA OOM errors where you try to put a big gradient through the thing and it, out of memory, program's crashing. And so I can reason by analogy there where you're trying to import too much data and then it crashes compared to this thing that can manage it. And I feel like that's such a huge thing. Things would say like gradient accumulation in deep learning, which is kind of the analogy that I'm going to be using to reason about this. Like the way that it prevents you from the OOM error has been such a game changer with training big models with big batch sizes, and it sounds like a very similar thing with this. And so, from my understanding, it sounds like with the aggressive garbage collector, it might slow it down when you get to that limit, maybe because it's. So I think it's what you do is maybe you have like a 32-bit like placeholder, right? The temporary allocation is trying to kill those to make room for more data.
Yeah. So the slowing down is kind of an effect. What it does, it speeds up the garbage collector itself. So basically, the garbage collector, or the point of the garbage collector, is to for any kind of memory that was used temporarily in a garbage collected language is not freed immediately. Basically, the garbage collector just runs in intervals and collects all that memory so that it can be reused again. And the longer it doesn't run, basically, so the longer the pause between two cycles, the more memory piles up. And if you're getting close to your memory limit, then it basically has to run more aggressively. And that kind of automatically does that trade-off where you only have this many CPUs. And if your CPUs do more garbage collection, that means they do less other things. So yes, you kind of trade off a bit of compute power for more garbage collection power and therefore prevent running out of memory if it's preventable.
So does this help with, say, like large-scale load tests, get a billion vectors into Weaviate? Does this kind of thing facilitate that?
Yeah, exactly. So the higher your regular heap use, or I think I use the term long-lived versus temporary. So basically, the higher your long-lived heap or memory usage is, and that is exactly what happens in such a billion-scale case, because those billion vectors, they will use, I don't know, including the index, something like 1 or 2 terabytes, probably, depending on the dimensionality. So I think that the SIFT1B data set is something that we've played around with, and I think it's a billion vectors at 128 dimensions. And that's 4 bytes per dimension. So that is not going to calculate it in my head and embarrass myself on the podcast, but that is a lot. And I think if you take into account the space for the index itself, we ended up with something like 1 terabyte or 1.2 terabytes. And if you have these kind of massive limits, then it really helps if you can set your GOMEMLIMIT so that the garbage collector doesn't need this massive overhead, because even just 10% is 120 gigabytes at 1.2 terabytes, and that's a lot.
Wow. Yes, super interesting. We've got 3 main topics to discuss on improving the performance of Weaviate. So Dirk, thank you so much for coming on the podcast to explain these new ideas.
Yeah, thank you for inviting me. Happy to be here.
So could we start with what is a red-black tree? How is it different from a regular binary tree, and how does this help with Weaviate's performance?
I would just start with explaining what a binary tree is. So let's say you have a bunch of numbers and you want to find out if a number is on your list. And Like classical approach would be you just have a long list and you go through it and check every number, and that's slow because you might have to check each entry before you know it. And what you can do is you sort this into a tree. So let's say you have numbers from 0 to 100. You pick a middle node, let's say 50 as the root node. And then if you want to check if 7 is in your tree, you go in and say, okay, I have 50, 7 is smaller than that, so I take the left entry. And the left entry might be 33. And you go, okay, 7 is smaller than 33. I go again in the left tree until you are at the bottom and have found the 7 or not. And that lets you check if the number is inside with a lot less steps than compared with just going through a list.
Mm-hmm.
Now, if you create these trees, you can have problems if you enter objects in order. Let's say the tree is empty and you start entering numbers in it, and let's say you start with 1, then 1 is your first object, the root of the tree, then you enter 2, say, okay, 2 is larger than 1, so you go to the right, and the right child of 1 is now the 2. And now the tree comes, you go in, tree is larger than larger than 1, you go to the right node, which is 2, tree is larger than 2, you go to the right and enter it there. And you can continue on that until you're at whatever numbers you are. And then your binary tree is basically a list. To find any object, you start at the first and you go to the right until you're there. And so it doesn't improve the performance when looking up things and also when writing objects into this tree. And now the red-black tree is a self-balanced tree. So there are a bunch of rules associated with the tree, and then you rebalance the tree when certain things happen. So in the example, the example I just gave, it's you enter the tree, so you have then 3 nodes on the right and 0 on the left, so you just like rotate it around. That the 2 is the new root, and then you have on the right the 3 and on the left the 1, and then you have a depth of 1 instead of a depth of 2, and that makes it then faster than entering and reading nodes from it.
Super cool. And yeah, so around the 1.15 release, I will have a blog post. It'll probably be in the description of this video when it's released that'll visually describe this concept of how you rotate the trees, the red-black coloring. Maybe you're aware of things like visual algo, these ideas of the red-black coloring, how that lets you balance a binary tree. Before we go a little deeper into how binary search trees help with databases to look into IDs, can you tell me about your experience implementing this in Weaviate? What do you change? What kind of, like in the code base, the kind of open source database engine, this kind of topic?
So we already have a binary tree in there where you insert the objects at first. And basically the change was limited to the existing binary tree implementation that we already have. So basically, I implemented checks. Are the rules, just can't think of the word, is any of the rules not valid anymore? And if yes, do the appropriate rotation changing values around to have it balanced. So the red-black tree itself is an idea, I think, from the 70s or the 80s, so it's around since quite a while. But it works great, so
So all of this is implemented in Go.
Yes.
How long have you been programming in Go? What was your journey like learning it?
2 months. So I started working on Weaviate early July, and I started, I don't know, maybe 2-3 weeks before with my first Go code. But it's just surprisingly fast. Like I was unsure at first how this would go, but like it's really quick that you get into Go. That's a great experience.
Super cool. I think that's really interesting that it took you 2 months to learn Go, and this kind of open source database, upgrading little parts like binary tree to red-black tree, these kind of updates. Could we maybe step a bit into the motivation of the binary tree? So we say we have these UUIDs that uniquely identify every item in our database. It could be images, passages, paragraphs, whatever you put in in the Weaviate vector database. So the UUIDs, they get sorted in the tree. Is that the key idea for when you like how you use this kind of structure?
Would be an example. Let's say you have a UID that is just a counter that goes up. And then if you insert it, you would get exactly that behavior as I described earlier, that you insert the first object, that is your root, you insert the second object, that's your right child, third object, that's your next right child, and so on. And that just really degrades the performance when you add objects and makes it very slow, because every time you insert an object, you have to go through all the objects you added before you can write it. And for the next object, it's even longer. So it gets really slow, and yeah.
So I kind of have two things I want to take this in, but first, so say if you're looping through your data on the client side, say you've got Python code and you're looping through the data items and you're using that loop counter to construct the UUID. Is that the kind of idea where you 1, 2, 3, 4 and such that you get this
Yes,
right
exactly.
everything going on the right node? Does this also play with, say we have an inverted index and we have I don't know, age, or let's say some numeric value with a broader range than that. Let's say maybe we have income in some database. I don't know. We have a big set of numbers in the inverted index. Does the binary tree also help with that kind of lookup?
I'm sorry, I don't know that. Like, as I said, I just started, so I don't fully understand the journey of the object.
Let me set the stage better. That was a bad example. So with the inverted index, it's like the foundational idea is, say you have a textbook and you're looking for biology. You go to the back of the textbook, it says biology is on page 99, page 305, inverted index. So I think with numeric values, we can also kind of have this inverted index where let's say it's age and it's 1 to 100, you'd say 80, and then your database is indexed where you have 80, and then the customers or whatever it is that have that value 80. Could we imagine numeric values like that? Because age, say it's like 0 to 100.
I think you need something like a key that identifies an object. So you can store as a value whatever you want. So you could have 50 values with a given key. But I'm not sure if you could use it for what you have in mind. So in general, it is you have a bunch of objects that have a unique key, and you want to insert or get them out of a structure quickly. I think that's where you use these binary trees, and red-black trees are then if you have ordered writes. It helps you to keep the performance up.
Right, yeah. I can certainly imagine how that, say with Weaviate, when you're doing a near object search and you pass in the ID of the object to reference the vector of that object, having this kind of structure to quickly grab the vector, search with it, obviously sounds super useful.
Yeah, I think I'm not totally sure about this, but there is this, oh God, what is it called? HNSW? Did I get that right? I can't remember these amounts. It works kind of into the same direct. Obviously, it's a lot more complicated, but I would say the idea behind it is similar. But obviously, it's more complex and helps you to find it. But this is like the implementation where I worked on. It's really you get objects into Weaviate, you first store them, and then you do other things later. I don't think it takes part in the search or in the indexing later.
Yeah, that's such a fascinating connection between, say, tree structures for fast search or the proximity graphs, hierarchical proximity graph structure of HNSW. The way that we have these like symbolic structures to organize data for fast lookup, super interesting. And I guess my understanding of it is, if you do a near object search where you pass in an ID, you can use the balanced red-black balanced binary search tree to quickly get that ID, quickly get the vector. Then you take that vector on the road to the HNSW index to now do that approximate nearest neighbor. But so kind of stepping out of this topic, can we now talk about the second topic on our agenda, fewer memory allocations on filtered aggregations? Could we maybe begin with the filtered aggregations and kind of understanding the current memory overhead and then kind of what's been done to help with that?
Yeah. So maybe we do a filtered aggregation. So we're looking for a value that's, for example, near another an object entry in the database that's near another entry. And there was a lot of overhead involved in temporary allocations while doing this. I think something like, so we did a benchmark where we added 1 million objects to Weaviate, and then did an aggregation where, for example, would just count how often is this property there. And with this, we had, I think, 200 gigabytes of just temporary allocations that would happen while checking how many are there. And there were a lot of different inefficiencies, I would say, in the code that you could optimize. In general, like there's the stack and the heap, where we can store memory in Go, or in general. And if you store it on this, you can store things on the stack where you A, know how big it is, and B, it doesn't escape. So let's say you have a function, you allocate some memory there, and then you return it up the stack to whatever column. You don't know what's happening afterwards, so you need to have it at the place where it can dynamically grow or shrink, or the lifetime is not limited, and so it goes onto the heap. If you have a variable that you create in a function, you only use it in that function, and afterwards it's gone, you can put it on the stack where it's much cheaper to create and to read. And so I would say there were 3 or 4 different patterns that I noticed. The first one is the objects, we store them in long byte arrays. So it's just a long array of bytes in Weaviate. And then if you, for example, want to check, oh, I want to read all the properties from it. Then there was a library that was used. It was called binary.read, I think. And this just created lots of allocations for this process. So if you say, oh, I want to have, this is the buffer from which I'm reading, where the object is stored in. I want to read the first 20 bytes because they mean the ID of the object. Then you could tell that to that library, and it would give you those first 20 bytes, and would create a bunch of temporary allocations while doing that. It's nice to use, but that makes it slow. And so I basically created a little low-level library that just reads from underlying buffer how many bytes you want without any temporary allocations. And that, then use that library at different places and made it, somewhat user-friendly.
Yeah. So I'm sorry to be, I'll be rewatching this and hopefully wrapping my head around the idea, but maybe, so a filtered aggregation is, say we have 100 million passages in Wikipedia, say we're trying to average out the word counts of them or something like that, right? So that's a filtered aggregation. So each Wikipedia passage with its respective properties, like word count, is stored as like a byte string.
Yes.
So you can better hash out the thing that you're trying to filter on.
So basically, you have the whole object. Like the complete object is one long byte string, and there you have to get to the right place. So you basically get that long thing, and then okay, the first 8 bytes are the ID of the object. Then there's a bunch of other things, and then there is let's say the length of the key of the object. So you first need to go to the place where the key is. Then you read the key. Then okay, the next 53 bytes are the key. If you need it, you read those. If not, you just jump over it, and then you do that until you're at the place where the information is that you're looking for. And basically, with the old library, you had to read everything, and every read created many allocations. And now this new library basically allows you, okay, I want to read, like I know the next value, like the next thing I'm reading is, let's say, an unsigned int64. So you do read unsigned int64, you get that value back, and the internal pointer that points where in the buffer is jumps forward. And you do that until you are at the right place in the buffer where the information is that you need.
Super cool. So it sounds like it would be especially useful if you have, say, a lot of properties, like data objects that have several properties would especially benefit from this kind of technique. And maybe one more thing I'm missing in my understanding is, so the temporary allocations. So is that so you copy the whole thing? Could you take me through it a little more? Sorry to be not
Yeah.
getting it.
Okay. Let's start from here. Let's say we have an object and the buffer where everything is stored is 10,000 entries long. And then what was done before is those 10,000 entries were given to that binary.read library, and they would say, okay, read me the first 4 bytes, read me the next 20 bytes, read me the next 5 bytes, and so on. And each of these calls the library created in the library, so not in our code, but in the library code, a bunch of temporary allocations where they just created buffers for whatever reason. Like I haven't looked at their code, so I don't know it. And basically what's happening now is you have 2 choices. A is move the position inside the buffer forward without reading anything. So if you know, oh, the first 80 bytes don't matter because it is information I don't need, you just say move position forward, and the internal number that says, oh, I'm at byte 15 is just moved 80 entries forward. And if you then say, oh, I know now I'm reading unsigned integer 64, you call the read unsigned integer 64 call, and it then reads the next 8 bytes, interprets them in a way that doesn't use any temporary allocation, and returns you the value.
So having that precision on knowing that you're going to read a 32-bit value, that reduces. I think that makes sense. So that reduces the because otherwise you need to allocate the 64-bit.
No, you always you always need to know what comes next. So you have a format, and you know in my long byte array that describes the object, like the first 8 bytes are some ID, then some other thing comes, then this comes, and then the length of the t comes, which is an unsigned 32-bit value, and so on. And so you always know what to read. It's just, are you doing it in an efficient way or an inefficient way, basically? And this library was doing it in an inefficient way. I don't know why, and like I haven't looked in their code, but it probably does a bunch of other things. And for example, it works for files and for any buffer, which makes it really nice to use. You can use the same functions on like reading a file and reading some byte array, probably also network. Also, I don't know that. And now I created some specialized function, which does a subset of what this binary.read library does. But for us, it does what we need at this place, and it does it more efficiently.
Wow. So I guess the high level takeaway is that you can do these aggregations with less memory requirements. But
yes.
I'm so fascinated at how you're able to kind of go into the database code and make these modifications, even with 2 months of Go, and replace this library with this thing. It's really opening my thinking up about this kind of like open source database and the different components of the databases that you can improve on, from the balancing trees for the sequential writes to the memory allocations on these aggregations. Is super interesting. So can we now get into our third topic? So with less memory consumption with importing many parallel batches, I think just importing data. I love this topic, trying to better understand it myself. So I'm so excited to learn about what's new with this.
Yeah. So what we were doing up to now is like you have your client, and then you add data in batches to Weaviate, and you, for example, do it over a network. So you just have 5 clients that you run in parallel that each send their batches to Weaviate, and that get processed there. And what was done up to now is that for each batch that gets imported, a number of Go routines are started that do the actual importing. So if the first batch arrives, Weaviate starts basically a number of CPU cores, Go routines, and those Go routines then work through the objects that are in the batch and add them to the actual database. And the same happens for the second and the third, the fourth, and so on. So if you have 10 batches in parallel, you start 10 times your number of cores, Go routines that work in parallel importing those objects. And each worker has a memory cost associated with it. So every worker that started has certain things it does, and those need memory. So if you have then 10 batches, you have that 100 times. And so I've got that number from Etienne. I haven't measured it myself, but like he tried to import many objects. I think he said a billion, but I'm not totally sure if it was a billion. And at some point on a really big machine, like 40% of all memory that's used was from these workers. And at a certain amount of time, certain point, like the import doesn't get faster if you add more Go routines. So you just add more memory that gets allocated and used, but the total throughput doesn't get higher anymore.
Yeah. Wow. This is incredible. The thinking around if I want to import a billion vectors into Weaviate that I can distribute it across, say, 10 like uploaders. Could we talk about that idea a bit more? So, because it would speed it up. It kind of reminds me almost of like distributed training with deep neural networks and the same kind of, distributed data uploading. What else goes into a distributed data uploading with, imagine the red black tree balancing it isn't, there probably needs to be some kind of synchronization step, right?
That's a different point. So first you kind of center the objects to Weaviate, and then you put each object into Weaviate, and you have clients, let's say the Python client, and that just has overhead. And you can't send the data from one client fast enough to saturate like a big server where you have Weaviate running. And so if you, instead of just having one client sending data, you have 2 or 3 clients, then you come to a point where you really use up all the resources that the server has. So in my local test on my machine, there is no real point in having 2 or 3 in parallel. It doesn't make it like maybe a little bit faster up to a point, but then it gets slower. But if you have this remote setup, so you're sending over network, you have latency, you have throughput issues, then it can help to have multiple batches in parallel.
So maybe we could step through. So the memory overhead of each of the clients, what is it that the clients need to store that creates the overhead?
Oh, it's not the clients. It's these workers that take the object and actually add it to Weaviate, and they have some temporary structures where they like that's one of the parts I haven't looked at, so I don't know it yet. But they have some temporary errors where they check, I already looked at a bunch of other objects, and now the new object is different. But yeah, I can't really explain it. Sorry about that one. And so basically what we have done is now, instead of starting a number of Go routines with each batch that comes, there's a pool of Go routines that works on the objects of all batches. So let's say you have 10 clients sending batches in, then all the objects from these batches get added to one queue, and then the shared workers just take the first entries, add them to the database. As soon as one is done, it takes the next one. So you always have the same number of workers adding objects, and it doesn't, like the number of workers doesn't doesn't scale up if you have more batches. And so you are limited in the growth of memory usage. So if you have many batches, because you don't have this many parallel operations that are going on.
Could you tell me, limited in the memory of the batch? Could you explain that one a little more?
Yes. So each worker that adds the objects to the database creates some temporary structures. As I said before, I'm not totally sure what they contain, but they need some memory to do their work. So if you have 10, you have 10 times those temporary structures. If you have 100, you have 100 times those temporary structures. So if you now say, okay, I'm limited it to 10 or 20 workers that go in parallel, you limit the amount of memory they use while importing it. And only that there's kind of a trade-off. So if you have more Go routines up to a point, it gets faster. Let's say you would just one worker, one Go routine working parallel, then you would be much slower than you have 5 if you have a 5-core machine. But if you're going to 50, then on your 5-core machine, the 50th go routine won't help you adding things faster, but it will still consume memory that you can't use for any other things.
So the client is freer to go get the next day. So the network part is faster, and so when you have 50, that
no, like the clients stay the same, the network stay the same. What's different is how Weaviate, like in Weaviate, how Weaviate accepts the objects and then adds it to the database. So Weaviate has, instead of having 100 Go routines working parallel in the object, it only has 10 or 15 or whatever you put in.
Okay, because it needs less temporary structure.
Yes, you have less Go routines working parallel in Weaviate, so you have less of these temporary objects adding used. So you have less over memory consumption.
So then, as a result, can you add even more data to it? Like, because then you make it at the max.
It scales a bit better if you have many batches. Then it's a bit faster, not too much, but a little bit. I think the most important thing is if you're adding lots of objects in parallel, then just your memory is growing so much that you're running out of memory at a certain point. And this is what goes away or is lower. So you can import more objects with the same amount of memory.
Super cool. So I think that was a great coverage of the three topics of self-balancing red-black trees to improve the sequential writes, fewer memory allocations and filtered aggregations, and as we just finished up on less memory consumption when importing many parallel batches. So quickly touching on a couple other topics in the 1.15 release, we have two new distance metrics, Hamming distance and Manhattan distance. Etienne, could you quickly explain what they are and how community members have contributed this?
Yeah. So first of all, the fact that community members have contributed, I'm super proud of that fact, because for an open source product, it's so nice to get these kind of outside contributions, and users having those use cases and knowing that they need them, and then they don't just have to put in a feature request, but they can also just do it themselves. That's really nice, and it's really cool to see that kind of community usage. So Manhattan distance, that's one that I haven't actually used myself before, but I like the naming. I think an alternative name is like taxi cab distance, and the idea is that you have a grid or like a city grid as you would have in Manhattan, and you can't just walk straight through a block. So basically, the only way to navigate from point A to point B is to actually walk the grid, basically, and the grid then would be your axes in the coordinate system, and that's basically what the distance is. So instead of taking the diagonals you would in Euclidean distance, you just take the sort of walk along the axes. And I have no idea what use cases are there for, what models use them, but apparently there are some, because our community members like them. Then Hamming distance is one that I'm a bit more familiar with, because that's also used for binary passage retrieval, where basically Hamming distance just gives you the different bits or bytes, or depending on what it runs on. If it runs on numbers, then it gives you the difference between the numbers of each vector. And on binary passage retrieval, the general idea is that you compress this entire vector into this kind of binary thing. And then instead of, let's say, with cosine calculating the entire angle, basically you just walk through all the bits and see, are they the same? Are they not the same? And if all the bits are the same, then the distance would be 0, and the vectors, or the binary vectors, would be identical. And basically the worst possible score that you could get is that every bit is different. So I guess it's in computer science terms, it's basically an XOR kind of calculation between the two vectors. And if all are different, then your maximum distance, basically the number of bits, or if it's on a number, the vector dimension, and then that would be like the most farthest apart vectors. Binary passage retrieval, ascent would be one of the use cases.
Yeah, the new distance metrics are so interesting. I think we've covered 5 things now, with cosine similarity being the foundational one, and then kind of dot product, where you remove the normalization from cosine similarity, then Euclidean and Manhattan, which are similar kind of analogs of each other, and now this Hamming distance thing, which I think is pretty unique. I remember doing bioinformatics classes where you look at like the RNA of mutated coronaviruses, and so you'd have this edit distance with the ACGT vocabulary, and so the edit distance, and maybe the binary passage retrieval may be looking for these connections. And Eric has been really studying these distance metrics and trying to prescribe things for Weaviate users, like when to use which one when. And so looking at things like accuracy and speed, I think you have the little reasoning around the speed where the Manhattan should be faster because you just have the differences. You don't need to square them. Some of the dot product, you don't need to normalize them. So it should be like a little bit faster. But generally, I think the prescription is, just try it and see what you're feeling is our current thinking. So we also have these two new HuggingFace modules, or two new modules that I think integrate with HuggingFace. Correct me if I'm wrong in saying that the kind of HuggingFace modules, but can you explain what are new about the new Weaviate modules?
Yeah. So one of those is actually completely Hugging Face specific. So Hugging Face has an API where you can basically it's a paid service from Hugging Face, and basically they host the model for you, and they do I think it's called the Hugging Face Inference API, and that's exactly what it does. So with Weaviate modules, or before, all that you could do with Weaviate modules is basically spin the module up yourself. But if you maybe already have a Hugging Face a subscription, you just want to integrate with that because you're already using that and you're happy with it. The new module basically just gives you an integration point to their API. So this is we call this, from the Weaviate's perspective, it's basically a third-party integration, because it's from a technical perspective, it's just a network call to this third-party API. But yeah, it gives you completely new flexibility because every model that is supported on Hugging Face, you can run it through Weaviate, and you can basically make use of all of the optimizations that the Hugging Face team has been doing already. So if you are, for example, self-hosting Weaviate but don't want to self-host the inference part, that would be one option. And of course, also with the Weaviate cloud service, you can integrate it as well. So you can, if you want a fully managed option, then you can integrate it as well and have basically the database part being managed by Semi and the inference part being managed by Hugging Face. And then the other module that we have, which is yet another community contribution, which I'm super proud of. It's a summarization module, which basically it runs at runtime or at query time. So similar to our Q&A module, for example, which I think we call the category readers and generators. And yeah, basically it takes your results, and if you want to, it can summarize results for you into something, into a shorter segment or so. So if you run your search results, for example, on very large documents, but you want to preview them, let's say in on your search results page, maybe that's a very simple and very much search related example. You could just generate such a summary on the fly and display it.
Awesome. Well, thank you so much, Etienne, and everyone. We have, again, this recap of cloud-native backups, improved stability for high memory setups, faster imports for ordered objects with this self-balancing red-black tree, more efficient filter aggregations, and then the two new distance metrics and two new Weaviate modules. So I'm like a kind of like a MC of a show now. So following this is the conclusion of our version 1.15 release. Now following is going to be some more information about Dirk. How did he become working with Etienne on these performance improvements? What is his background like? What led him to be thinking about these things? So I hope you'll be sticking around to watch that part as well.
Thanks for having me.
Dirk, I'm really curious, like how has your kind of career development been that you can identify these performance bottlenecks and develop things like this?
I was a physicist, so I did a physics master, PhD, and a bit of postdoc, and I basically wrote simulations about various topics, and it's just natural to look for these performance optimization when you write these simulations. And then my last job was at Deutsche Bahn, which is like a train company in Germany, and as part of a team that wrote a simulation for microscopic train simulations. So I did a lot more architecture and general design things. There was always this performance thing in the back or a part of the work.
Can you tell me a little more about like simulation code, and kind of what the experiments look like for that?
It really depends. So I would go to university again because I think I'm not allowed to tell too much about my last job. So what I did there was like cell simulations. So how do cell moves? How do they interact, and so on. And in one of these projects, for example, we had a lot of noise, how the cells would move. So that like we were looking into collisions between cells, and you have them on a 1D stripe and they collide with each other. And we had a little bit of noise, so they don't always go head on, but like this sometimes, so they rotate a little bit. And so you need a lot of With the same parameter sets, you need many runs, so you can do some statistics. If you just do one, it could be random, the outcome, but if you do 1,000 for this parameter set, and then, oh, this case happens 20 times, this case happens 50 times, then you can build a statistic and you can compare different parameter sets. So your code needs to be fast enough to explore the relevant parameter space and have enough runs so you can build up statistics. And so, yeah, it needs to be fast enough for that.
Wow, yeah. Can I ask about what inspired your interest in Weaviate?
It's a cool project. So I talked with Etienne about it, and it sounded really interesting. And I thought I did simulations for 10 years, 12 years, something like that. And it's time to move on and do something different. And I was very close to machine learning in my last project. Didn't do it myself, but built a simulation that was then used with machine learning. And so I feel like I'm keeping this closeness to machine learning, but not doing it myself. And yeah, all sounded very
So,
interesting going from the big corporate company to a small startup.
oh yeah, I'd love to talk about that as well. If I could stay on one more thing with what is the role of machine learning in those simulations that you described?
So at university, there was no machine learning, so I did experiment a little bit with detecting the outcomes, but it was just very, very, very simple. In my last job, basically the goal of the project was to automate scheduling, like long-term planning and short-term planning. So long-term planning in the sense of the next schedule, how all of our trains drive the network for the next half a year. And we have these requirements of train companies that want to drive from here to there, from there to here, and so on, and get a schedule where everything fits in. And the second part, short term, let's say tree falls over, you can't drive over those tracks anymore. We need to reroute everything. How can we do it while staying as close as possible to the original schedule and making our passengers arrive as close to the original time as possible? And so I was building with my team this microscopic train simulations. And then there was another team that used reinforcement learning to try to learn with the simulation how to create conflict-free schedules and to react to risk disruptions.
Hmm. Could, is there any scenario in which that would be like the Weaviate data uploading would be so chaotic that it would be an analogous kind of system, or is it too?
I thought a bit about it, but I I don't think I don't think there is a direct connection. I think reinforcement learning, not too much into it, but it's I think very niche and special. I think there are problems where it fits great and many where it doesn't. Um, yeah.
So sorry if I'm. So it's like these really complex scheduling algorithms. Is I guess I'm curious if Weaviate to say there's a million clients uploading data, and then you got to synchronize it all, get it in the database. Is that maybe analogous, or is it?
I don't think so. No, because yeah, basically the problems you have in the train system is that trains cannot easily overtake each other. So the order trains are in at a certain point in time is really important. And you can have a train, I'm not using German cities, but let's say one train starting in Munich, another train starting in Berlin, which is 500 kilometers away. And they would need to use the same piece of track in 5 hours. So the order in which it arrive at that point, if the high-speed train comes first or if the slow cargo train comes first, really can mess up your schedule, because if the high-speed train is behind the cargo train, which drives really slow and can't be overtaken, then you have the high-speed train behind it going really slow forward. And that's a real problem that can't be solved with analytical methods. So that's why we went the AI route. I think with Weaviate, this uploading is you have a bunch of data, you need to get it into the database, and the order doesn't really matter, and you just need to make it efficient. And yeah.
What do you think about this idea? Say we have video data, right? So video data could be a 30-second video is the bullet train, it's it gets right in compared to a 3-hour video where right? Would that kind of thing maybe be similar?
I don't see a connection there. Sorry. Um, yeah, I um, I think this scheduling is so difficult because you have everything affecting everything else. So each decision you do at one point can have a day later an effect somewhere else that you don't know immediately. And with like adding things to Weaviate, the objects don't depend on each other. You need to get them in without having bugs in your code, like without overwriting anything else. But besides that, they're independent from each other. And it doesn't really matter if you add a 30 minutes video or a 30 seconds video. Like the process of writing it will probably take longer because you have more data. But I think besides that, there is not too big of a connection.
Sorry to stay on. Maybe with the cross referencing, there could be some kind of, because I think with the cross referencing, the current way that you need to do it is you kind of have like a parent child import where first you import, say it's articles and then they have their paragraphs. You need to first get the articles in there and then you reference the paragraphs.
Yeah.
So maybe with these graph structures, there's some kind of scheduling to how you orchestrate the referencing with uploading.
That could be like if it's really complex and you have like circular things that you need to break up, and there it could be. Um, well, maybe let's say you're creating objects on the fly, and then you need to make sure that everything is in that you need, and then a new object appears, and then you need to reorder everything. If you have that, then it might be, but I'm not sure how realistic, like how often that happens. Maybe, but
Right. Super cool. So, can you tell me about your experience at Semi Technologies and this kind of the earlier topic we previewed of working in a big corporation compared to the startup?
yeah. So I was like in the startup in a big company, but then the how should I say it? The big company came into the startup, and so yeah, meetings, corporate overhead, and that was sometimes a bit too much. And now I would say it's very lean. You really work most of your time. Obviously, you talk with your colleagues sometimes here and there, but you really have time to work. So that's um, a very nice change, and like you still have the feeling that you know everyone. So like in the old like we grew, like I think when I started we were 60 people, and when I left it was 250. So I kind of you don't know everyone in the company anymore, and now I have the feeling I know all the names and all the faces. Um, that's a little
Super cool.
different.
So, if I ask one more question about sort of your motivation and kind of do you maybe have like an application of Weaviate? Like personally, I love the idea of searching through scientific papers, and I find every little thing I'm working on in that application to be very motivating. Do you have that kind of thing, or is it just about the technical of where can I
Um,
find it in performance?
like like personally, I really like to code and to complicated problems. I guess now when you said scientific papers, if you have a lot of results from science, like you do experiments or you do simulations, and you have just a bunch of results that you can't really look at anymore, to have a possibility to just like send it to Weaviate and do some basic analytics in there. Like as I said with my simulations, where you have the cells crashing head on, and I looked at a lot of videos and I wrote like by hand the script that if the cells are after colliding are this far away, then it's this case, and yeah, that was a bit annoying. So if you could automate that and have Weaviate in there, that would be really cool. And I'm sure in larger projects, I did it. I mostly worked alone with one or two colleagues, so we didn't have that much data. But if you're in a big collaboration, let's say at CERN or something, where they have billions of terabytes, if you could help there, I think that would be something that would really fascinate me.
Yeah, wow. That, it's outside of something I thought about, but that kind of like how cell simulations. I've heard of like maybe like docking simulations. I don't really know too much about this, but this kind of you're simulating a bunch of like is it like electromagnetic interactions, like that kind of thing? And
Uh, so we did like effective interaction. So we didn't go into the like the physical details that the electrons that don't want to be at the same place. But basically, if the one cell is here, then the other cell can't be here, and they have some chemical attraction to each other, and yeah, repulse each other at certain places. So it was very how do you say, like high level. So we didn't go into the details because it's already like the model's already complex enough. So you really need to think about what can you put in, what's like the minimum level of detail that you need to have in there to kind of simulate what's happening in the experiment.
Wow. So you have like a big molecule and some kind of chemical score
No,
to it rather than like an
we
atom level.
no, we did like real like biological cells. So and we simulate them as a blob, and we used, it's called phase field approach. So it's basically a field that's between 1 and 0. Where it's 1, there is the cell. Where it's 0, there it's not. And it goes like it's 1, 1, 1, 1, 1, and then it goes down to 0 in like a very small area. And in this fuzzy in between phase, that like it's the boundary of the cell. And then these phase fields from different cells can get close to each other. And when kind of their boundaries touch, you have like physical interactions. So they repulse each other and attract each other in a certain way. And then based on some chemicals inside of the cell, you have additional chemical interactions. And then if you let them collide, you have, based on these interactions, you have then the cells behave differently. And and there were like interesting experiments about it, and that's what we tried to reproduce, those experiments.
Yeah, wow, that sounds super interesting. Like that, like hierarchy of biology and the that whole thing is super interesting. Well, Dirk, thank you so much for describing the new performance changes in Weaviate version 1.15, and I really enjoyed getting to learn more about your background and the things that interest you. I really enjoyed this podcast.
Thank you very much. Enjoyed it too.